May I start, Sebastian?
Yeah, sure, Muammer.
Let me just ask some simple questions in the beginning because I missed some point on the slide 18 of your presentation.
You are serious? You took the numbers of the slides?
Yes, I think it's easier for. So for the dispersion, I see on the left, K2H is the wave number in the other direction, right? This K2.
Right. So it's the wave number in the vertical direction.
And the one parallel to the lamination.
The one that is parallel to the one that is along the lamina, right? In this direction.
Okay.
So it's not in the lamination direction, right?
If you could, just to be sure, if you could go one slide back.
Yeah. So let's see if this works. Let's see. I connected with my iPad, so let's see if this works.
Yes, I see it.
So this is X1, this is X2. So K2 is this.
Okay, so then you fix a given K2, and that's why you get this like zero frequency gap down.
Yes, we have, exactly. We have a zero frequency gap. You are sharp, yet you notice that near zero frequency gap. So actually, Willis also observed that in the antiplane problem. I just want to mention that we are not the first that are reporting this band gap at zero frequency, okay? But yeah, this is what we have here.
Okay, thanks. Then similar to that on the slide 21, when you talk about basically the derivative, yes, so basically for this propagating this P, the d omega over dk, here your omegas are complex, right?
No, here omega are real. So this is what I was saying by, I don't know, maybe, I hope I'm not saying trivial things, okay? But we need to relate the mathematics to the physics of the problem, right? In what sense? Now the problem that we are considering, like I showed you later on, I'm thinking, for instance, on a setting where I prescribe here some source, and this source acts with some frequency, and I'm asking what will be the modes that will evolve in this laminate, right? So here, the prescribed quantity is omega, the real frequency, and there is no dissipation in the system, right? Why would omega be complex, right? I'm having a source that acts in a fixed frequency. So the question is, what will be the wave numbers in the laminate? The evolution here, right? This is like the unknown quantity. I'm prescribing omega, I'm prescribing K2 because the wave here comes with some angle, so it will have some wavelength in this direction. So these are the prescribed quantities, and the unknown is KB. So like I said, we need to relate the mathematics to the physics, and in this sense, this is why I also noted in a nutshell that we can think about a dual problem. So actually, the first introduction of that problem that I saw was to Willis. So he conceived the following case, where we have this as the laminate, right? And this is, and the homogeneous F-space is below. So you can think about an incident waves that come from here. And in this case, we actually control the wave number in this direction, right? Because these waves hit here, and this is, in this case, we control KB. And the unknown is K2, is how the modes will evolve in this direction. Does this make sense?
Yeah, no, clear.
Okay. And now a different question would be, okay, let us again think about the infinite periodic medium, and let us apply some initial load or deformation or velocity, and let it have some free waves, right? And this is a different question. But which correspond usually to what will be the omega, what are the natural frequencies. But that's not the question that I'm asking here. Does this make sense?
Yeah.
Can I just ask a last question, Sebastian?
Yes, please do.
On the slide 3940, so basically when you were talking about this Willis coupling and, for example, the piezoelectric in this kind of problem, what are the relative, let's say, scale lengths for the effects? For example, if I look at the Willis coupling, I could relate it to some, let's say, length of the wavelength compared to my unit cell, and then the similar would happen to the piezoelectric stuff. What are the different scale lengths in this kind of stuff? Is it something that you just consider hypothetically in, say, material? I have a material and I can arbitrarily choose the piezoelectric coefficient inside, and the material are already piezo by constitution?
Yes.
Because is that the case?
Yes. If let me try to answer, and if I understood you wrongly, then correct me, okay? So let's say we have our theory. Not let's say, we have our theory, okay? And we apply this homogenization theory to, let's look at two cases. This is one case. So this is a piezoelectric composite. We have fibers that are made from one piezoelectric composite, one piezoelectric material that are embedded, if you will, in a different piezoelectric material. I think we can also embed it in non-piezoelectric, but for the sake of simplicity, think about it as another piezoelectric material. And now I ask the question, what is the relation between the macroscopic fields in this periodic medium? Okay? And we show that the effective fields, again, the effective fields, we also need to quantify what do we mean by effective fields, okay? There is some definition for that, right? But let us say that the effective fields are what we get when we average the periodic part. That if this is periodic, we have block form, right? A periodic functions time and envelope. So let's say that we average over the periodic part and we keep only the large wavelength. If the Bloch wavelength is indeed the large wavelength, these fields are related to what we showed earlier, in the same way that the Willis coupling emerged when we homogenize over elastic composite. Does this make sense?
Yeah, I was just confused because to start with the piezoelectric material, if you say here you have two of them, so then the material is both of the components are anisotropic in a way, so they have certain anisotropy. And I was just wondering how you average them, or you consider isotropic piezo effect.
Okay. Maybe I'm not understanding you, but I'm not averaging over the composite. I'm averaging over the resultant fields, and then I relate the resultant fields. And then I say what relates the resultant fields describes the constitutive relation. I'm not averaging over the properties that I have here, right? That's not how we do homogenization, right? So it's not what I'm doing. Listen, this is a topic that I can talk on for hours, okay? But I want to say that let's call this rigorous homogenization, okay? Where I have some unit cell and I'm asking how an infinite periodic repetition of this unit cell will behave on a macroscopic scale, okay? And in this case, this is some argument that I had also in Milton, but in this case, if I don't have any, let's say, sources in the problem, then the effective description is not unique. I can also, in some sense, absorb the cross-coupling to the regular couplings. I can absorb, if you will, what I call W into the piezoelectric modulus, or I can absorb the Willis coupling, let's say, into the stiffness, because these are in general non-local operators. But if you do this and you look at the properties that you get, these properties violate certain conditions. For instance, if we look at the dielectric tensor, its diagonal terms must be real. in order to satisfy reciprocity, if I remember correctly. And if you do this, you don't get it anymore. You see what I'm saying?
Yeah, no, that's clear now.
And this is like to do this, we went through hell, okay, to like homogenize this. This is a lot of math and so on, you know, all kind of a headache. But we can also do something that we call how did you call it? Give me 1 second. Okay, I don't remember the name and I don't want to waste time, but let's say we have a rigorous homogenization and we have non-rigorous homogenization, okay? So when I mean non-rigorous homogenization, I mean that we look at an assembly. Okay, is the sharing works?
Yes.
You see the screen?
Yes, we see the screen.
Yeah, so let's think about, for some reason it doesn't, just 1 second, okay? Sorry for the, that's not this. Okay, so we can look at, for instance, 3 piezoelectric layers, okay, like one stack, okay, look at one stack, connect it to 2 waveguides and ask what are the scattering properties. And then we ask the question, what is the homogenized medium that will reproduce the same scattering properties? So this is not really rigorous, right? We are not doing all this thing. We just look at the scattering properties. And the same phenomena that I mentioned earlier with regard to the properties of the effective, the properties of the macroscopic description, the homogeneous description, appears also here. If we do this homogenization without like the generalized Willis coupling, we call it electromomentum coupling, the properties that you get are not physical. Again, you have an imaginary component here, or you get different results when you carry out your measurement for left incident wave and right incident wave. These phenomena were also reported when, for instance, the group of Haberman and maybe Lou, but I'm not sure of, did that when they analyzed conventional Willis materials, right? They took one element, they did some scattering experiment, and they showed that without this S, the properties that you get are different from one experiment to another, right?
No, it's a clear. Thanks for answering.
So I've got a question from Mohamed Farhat. Is it possible to have the same gain-loss effect for bending waves?
For bend, you mean flexural? Flexural waves?
Flexural, yeah, in thin elastic plates. Could you end up with the same kind of, you know, effects, overall effects that here seem to occur in 3D bodies? So essentially, you lose one dimension. You make your elastic body very thin.
Yeah, so okay.
I mean, you certainly have also all kinds of piezomagnetic thermoelastic governing properties.
No, I like the question. Let me try to answer it, okay? So there are 2 things. I can answer it from a mathematical viewpoint and a physical. I'll start with the mathematical, okay? On a basic level, let us first think about the antiplane shear problem, okay? And in the same way, let us think about the electromagnetic problem, okay? Why they don't have exceptional point there? Why they don't have these type of degeneracies there? Because, again, very basically, if you look at the transfer matrix, they have a 2x2 matrix because you have, if you will, only the electric field, then it's the derivative, okay? These are the fields that you are propagating. And the properties of the transfer matrix are such that you either have the eigenvalue and its inverse, or the eigenvalue and its complex conjugate as solutions. You can show that there is some property. Okay, you have like a lambda, lambda star, and lambda minus 1. And then you either have that the KB, the Bloch parameter, is either pure real or pure imaginary. You can't get any complex values. It comes from this. Okay, now in our problem it's different because we have, again, both longitudinal and transverse mode as our basis. And again, very basically, we have a 4x4 matrix. And the argument that I just mentioned no longer holds. So we really have genuine complex eigenvalues. And then we can tune the system and make them degenerate, okay? Now, again, on a basic level, for flexural waves, the transfer matrices are also a 4x4, right? We have like the deflection and the angle and the shear force and the moment, right? So I think that we can have that. And in this case, maybe I need to think about what are the modes that are going to be degenerate. In our case, again, it's like a generalization of shear and pressure, but maybe in bending waves, maybe it will be, well, you said very thin, but maybe it will be antisymmetric and symmetric with respect to the midplane or something like that. So there is some potential, and this is interesting, and maybe this is worth looking in. So, Mohammed, you said that you don't have a mic, but I hope that you hear me, so thank you for the question.
Okay, very interesting. Regarding the homogenization process, does it resemble, you know, ensemble averaging? I mean,
exactly ensemble averaging. This is ensemble averaging.
Okay.
And this ensemble averaging in the periodic case, it's easier to explain it in the periodic case. Ensemble averaging in the periodic case reduces to averaging over the periodic function, the periodic part of. So again, if we have a periodic medium, right, three waves. So let's say the solution U, right? It looks like some periodic function with the periodicity of the unit cell times EIKB x. Let's think about 1D, right? So what we call effective will be the average over UP of x times EIKBx. So this is what the ensemble averaging reduces when we have a periodic medium. This is how Willis defined his framework, and also Alu, I think, later on. And there is also an excellent paper by Nassar.
Yeah, Hussein Nassar does this kind of stuff, yeah.
And then they talked about the meaning of this, because in a nutshell, the idea in what we do here is to keep the largest wavelength, right? Because we have like some envelope with this KB, and here we have some fluctuations, right? But if you go outside the first Brillouin zone, then this is not necessarily the largest wavelength anymore, and they discuss it, and it's an excellent paper.
Okay. We've got one new message. Thanks for the answer and the nice talk. So from Mohamed. Right. Do we have any more questions?
I have a question.
Yeah, please, Emile.
No, this is Michele. But if Emile? Okay.
Okay, Michele. Hi, Michele.
No, but it was Emile before.
Okay, thank you. And first, thank you for the very nice talk. If you can remind us, what are the parameters we have control over? So as I understood, it's K2 and omega. These are the two parameters which we can control, especially in this simulation, and this is what you will work with.
Okay, so sorry.
Yeah, they are both real variables. So my actually real question is, how much of this Riemann surface can we explore with just these two parameters, omega and K2?
Okay, so let me try to answer the question. Let me try to answer the question.
So you had this very nice, when you answer Maumer question, you draw this part of the wave which is parallel to the interface, and you said that fixes the K2.
Right. Okay. So let me first go back to the mathematical formulation. Let's first think about the mathematics of the problem. And the mathematics of the problem are such that this transfer matrix, which governs the spatial evolution, is a function of the following parameters, right? So it's a function of K2, and like I said, the frequency, and in turn, they are all related to the dispersion to KB, right? And I said, okay, let's try to relate this problem to specific boundary value problem. And I said, indeed, that if I think about the following configuration, I can think about some source here, and I say that this source is acting with some real frequency omega. All the constituents are conservative in the sense that there is no dissipation, no loss, so the omega won't decay, right? And I said that in this case, indeed, I fix KB, I fix K2. So in this setting, K2 is real. So again, if I'm answering your question, when I think about the Riemann surface, in this surface, when I think about that problem, I can only go across
the line.
Yes, I can only go across the plane where image K2 H is 0, right? I don't have, in this problem, I'm going only in this.
That's right. That's right. So you can miss the exceptional point. So you need a little bit of tuning to put the exceptional point.
No, but here, no. Okay, but here the exceptional point is in this space.
Yeah, right? That's right. It's on this line, you mean?
In this plane. I have a plane for image K2 H is 0. I have this plane, right? So the exceptional point is part of this plane, right?
Yes, that's right. But it could have been sideways.
Right, you are right. There are also other exceptional points. Okay, so now it's a question of what do we term an exceptional point, right? If you ask a mathematician or a physicist or whatnot, okay? So if we are talking about the transition of propagating mode to evanescent mode, then the exceptional point must lie, in this case, on image K2H equals to 0. But if you think about other degeneracies, non-Hermitian degeneracies, they indeed can happen not for, and this is, for instance, what we see, this is, for instance, let me clear the screen. It doesn't work. Oh, it works. This is, just a second. It doesn't work. Okay, now it works. This is, for instance, what you see here. This is also an exceptional point. We have the degeneracy of two imaginary parts, but it happens for a non-zero.
So you cannot access those. Will be very interesting if somehow experimentally we can access those. I don't know how you engineer a arbitrary imaginary.
So why are you interested? We can talk later because I have some ongoing work that is related exactly to the questions that you are asking.
I can tell you in a, so, you know, in 1956, Walter Kohn published a really influential paper on analytic structure of block waves in just 1D. And he asked the question, what happens with this K vector when you allow it to be complex? And he discovered this Riemann surface, which is very specific to 1D. Your colleague, Yoshi Avron and Barry Simon found this one very interesting and tried to generalize to higher dimensions with some limited success. And while I was working with Walter Kohn, my job was to actually do the same analytic structure for quasi-one-dimensional systems, which means exactly systems which have not just one mode of propagation, but various modes. And I discovered that there is a whole beautiful Riemann surface which can be absolutely and completely described, and one can see where these branch points come from, and you can get immediately an idea how the whole structure of the Riemann surface looks like. But and then you discover that they are quite close to the real axis. There can be a large number of branch points, which in fact influence how, for example, the one-year functions decay, how the asymptotic behavior of the Green's functions, and all of that. And unfortunately, nobody knows how to access these complex K vectors. I mean, to access these branch points, which happen somewhere on the Riemann surface, but it will be really interesting to.
But mechanically, why would you be interested in them? Because these do not correspond to propagating waves, right? So, like, why would you be interested in accessing?
So, yes, somehow, if you go around, when you go around, you get topological numbers and stuff like that.
Yeah, but okay, yeah.
Okay, great. Yeah.
Oh, there was one more question. Sorry for taking so long.
No, it's great, Emil. So, Michele, can you put forward your question?
Okay, thank you. Hello. Gal is connected with this discussion. I would like only to be a little bit more physical. So you need a system in which you have two types of wave propagating at the same frequency, and the, let's say, dispersion curve has to intersect. We have discovered not only at the boundary of the Brillouin zone, but also in other points. This is physically the source of the effect.
Sorry, I missed the question. Well, what was the question, Michel?
Okay, so you need to have two types of wave propagating at the same frequency at the end of the day, and they have to intersect in some point. Just to summarize as much as possible.
So what do you mean? You mean like what is the takeaway from the talk?
What is the source of this particular effect of this exceptional point? So you have to find a system in which you have two types of wave different that intersect at a certain point in the dispersion diagram.
I think so, but I'm not really sure that I understand the... If you are asking if an exceptional point emerged in a system where you have...
if you have flexural waves, you have only one wave propagating, okay? And in elasticity, you have this shear and pressure wave, and then you can build an isotropic and so on. But you can make with this laminate the dispersion curve intersecting in at some frequency. That's all.
Yes, and then what happens is the splitting of that degeneracy, which leads to these small gaps that you see in this graph, leads to exceptional points, which just move from the real axis a little bit up and above.
Okay.
So that's the splitting of these degeneracies and opening of the gap is the source of these exceptional points.
But this is connected with the Dirac cone, or has nothing to do?
So a Dirac cone is a Hermitian degeneracy in the sense, I have a slide for that. It's interesting. It's a good observation what you just brought up. Okay, so a Dirac cone is what you see here, right? It's a Hermitian degeneracy. And here, let's say these are the parameters of the system. If you perturb one of the parameters, say any parameter, then the splitting, let's say if the value that you're looking at is now the frequency, the splitting goes like a linear function, whereas near the exceptional point, okay, the splitting goes like a square root. If you have two modes,
Yeah,
you take the
or
square root.
parabolic in the other. Okay.
Now, one comment with this regard, there is a work that shows that if you have a system with a Dirac cone and you somehow edit gain or loss, then this Dirac cone is being deformed to a ring of exceptional points. You can take this and deform it and you get some number of exceptional points. So actually, one can think of the Dirac cone as the limit of these exceptional points when the measure of non-hermiticity goes to 0. I hope this makes some sense to you.
Yes, thanks.
Okay, great. So effectively, Emil suggests a paper in Physical Review B, Analytic Structure of Block Functions for Linear Molecular Chains.
Yes, which shows how these branch points appear by splitting dispersion curves. Once you fix K2, then they all appear in this way.
Okay.
Yes. When we will see experimental results, that will be. Are you planning in the near future?
I want to, but actually I talked with Sebastian colleague. I don't know where it stands now with Patrick Seba. We thought about trying to realize some of the things that I mentioned, but I need also to hire. You know, I'm looking for people that will do experiments. I cannot change the lamp in my office if it goes bad. So my hands are very bad. I cannot write equation, you know.
So you mean
people, yeah.
So you are building a theoretical and experimental lab over there?
I'm looking for someone to do experiments with. Yeah, I would like to do that.
So at Technion, there are no groups which do vibration?
Yeah, there are. There are. I need to push forward this more. Because maybe we can talk later, but there are like really nice works that people have done with regard to exceptional points in microwaves and stuff like that. And to do that in mechanics, I think it will be, you know, regarding encirclement of the exceptional points and stuff like that. Maybe we can talk later. I can show you what I have in mind, but
yeah, sounds very interesting.
So Emil, the paper you suggested, so can you explain in layman terms, because what is the relevance with metamaterials? I mean, it's
the relevance. I can give you one quick relevance. For example, in strictly one dimension, we can calculate. We have an expression, very convenient expression for the Green's function in terms of the Wronskian. You use the decaying function to the left, solution to the left, right. You assemble them using the Wronskian. You wonder how that can be generalized to higher dimension, or maybe quasi one-dimensional. That formula can be actually derived by integrating on this Riemann surface. And once you have the Riemann surface, then you can repeat the same and you obtain a closed form of the Green's function for a quasi one-dimensional system. So basically you have an analytic expression of the Green's function, which then you can carry on with, for example, calculating transmission matrices. And we use this Green's function when we did molecular electronics to just calculate tunneling conductance and so on.
Okay, I think we need a bit of time to digest this paper, but we will certainly read it with great interest. Okay, so and this paper you think can be generalized to because here it's Schrödinger, so it can be generalized to elasticity, to vector problems.
At the end, the approach is very simple. You have a Hamiltonian which depends on a parameter.
Yeah.
And I mean an operator, and this operator is Hermitian while this parameter goes on a circle, and you ask, and it's analytic as you go from the circle, and you ask what happens if you put this parameter going inside the disk. And then one shows that if you start from for example, one single wave operator with one single mode has a very simple Riemann surface. It's just a helix which goes on and on with the fundamental branch point, logarithmic branch point in the middle. So when you put two waves together, two waves mode, then you have two such Riemann surfaces, and occasionally when dispersion curves intersect, and these Riemann surfaces get connected at one point. When you couple the two modes, then small gaps open, the dispersion curve split, and then on this Riemann surface, what happens is a branch cut appears, and two exceptional points form, moving away from the from the circle, one inside the disk, one outside the disk. And then if you start from this picture, when you have waves which involves more than one mode, and you start from decoupled picture, then by just looking at the intersection, at the points where the dispersion curves intersect, you can derive immediately what is the structure of the Riemann surface. You can be sure that every time when such an intersection point appears, then the two disconnected Riemann surfaces for each mode get connected through a branch cut, and you can move from one to another. So it's a very simple and general picture.
Okay, lovely. Gal, I was meant to ask you, you use finite elements. It's a commercial finite element package. I mean, it's COMSOL. I mean, how do you do your numerics usually? So you have the transfer matrix approach.
Yeah, it was what I showed earlier. This, where is it? Simulation. Yeah, this was COMSOL. Okay, and otherwise you using, I mean, your analytical tools. Yeah, so the solution earlier, like I said, it's a standard, if you will, normal mode decomposition. Yeah. The basis I constructed with the transfer matrix. We can do it also with the plane wave expansion to create the basis solution in the laminate, and then you just tailor the continuity conditions. For this problem is actually quite simple. Sorry.
To get the negative reflection there, what did you optimize?
So actually, I didn't optimize. I mean, I just I looked. Okay, I had a sense that I can get it because of the argument that I just showed you earlier, and then I evaluated a couple of examples, and then I saw that we get, like I said, the exceptional point. So this is just one diagram that I evaluated. I took a standard laminate in the sense that this was the laminate that other people had worked on, and I saw that I got it, right? And later on, I said to my student, okay, do different evaluation, and let's see how does this diagram look like, right? So for instance, the one that I simulated this. What do we see? Why this cut? For me, was supposed to deliver a negative fraction. Because look, the curve of versus K2 changes its sign. Right? The curvature here has a different sign. So this is like standard. So this will supposed to be positive. And this because of this change of sign, is supposed to be negative. Why? Why? Because, you know, if dk2 changes its sign, then also the omega dk2 changes its sign. It's like the chain rule or something like that, right? So this is like...
Yeah, oh, that's a great argument. So these exceptional points can give you a handle to control the curvature of the dispersion.
I don't know, maybe I wrote it, maybe I wrote it somewhere here.
Yeah, so it happened with just a
I found it. What I want to
ordinary laminate, an ordinary laminate. It just the two modes were coupled.
Yeah,
Very
so this
interesting.
is the argument. So the curvature, which goes like the energy flux, is actually the curvature of a cut of the Riemann surface. So tailor this and you tailor how energy will propagate.
That's right. It's I love it because
Simple.
you know, you show people and students that in fact you have to think beyond what you see with your eyes and you have to navigate in an abstract space to build effects and I use the words to interact with our observable universe. You can interact in so many ways, but if you take the ordinary approach, you miss so much. Yeah, it's a problem because our students, I mean, the students don't see why math is useful.
Yeah.
So do we have any more questions from the audience? So Michele wanted to thank you, Gal, for the very interesting meeting. Seminar.
Thank you for the interest, and maybe Emil, I'll email you and maybe we can chat.
Yeah, thank you.
Okay.
Yes, so I think with this we will bring this webinar to a close. I mean, this is really fantastic stuff. I think these are all exciting phenomena, and I really love the fact that you have this generalized Willis coupling with this extra layer, you know, of governing equation. Okay, so Muammer, can you remind me with our next speaker?
It's Yuri Kirshach.
Okay. So, right. So guys, I hope to see you next week in good shape. So keep away from COVID as per usual, as much as you can.